today's material, we're going to continue the properties of logarithms. Prior to today, we had a couple of properties of logs that we looked at last week. We said that log base b of b is 1. That was one of the ones we looked at, and log base b of 1 was 0. And remember, these points were pretty critical on the graph of an exponential and a log, vice versa, since they're inverses. Trying to remember what other log properties we looked at. Oh, and then we looked at the inverse properties, that log base b of b to the x brought you right back to x. So this is your exponential function. That's your inside function. When you compose it with your log function, you come right back to where you started. And then when you start with your exponential function and you put your log function in as the exponent, that also took you right back to x. So this was the inverse property of, the composition of inverse functions. Brings you right back to where you started. And these were two generic properties of logs. So we're going to continue with a couple more properties of logs today. So the first one has to do with, and let's just review exponents. Since logs are exponents, let's just review what exponent properties look like. Suppose I have this exponent problem. How would I simplify that using my exponent properties? What does that become? Almost x plus y, right? So when we have the same bases are the same, and we're multiplying, we have the multiplication, same bases, we add our exponents. Okay, so that's a review of that exponent property. What about if we have a to the x divided by a to the y? What do we do now? You do x minus y. You keep your base the same and you subtract your exponents. So if you take a look at these first two properties, hopefully you can see a relationship. Here I'm multiplying exponential form, I add my exponents. Here I'm dividing two exponential forms and I subtract my exponents. And since logs are just exponents, it says that if you have log base b of a product, x times y, you can expand. One of the terms we use is to expand this. You can expand this by saying that it's log base b of x plus log base b of y. When you multiply, you add your exponents. When you multiply, you add your exponents. Over here, we have log base b of a quotient. When we divide, we subtract our exponents. Since log base b of x and log base b of y are just a fancy way of writing exponents, we subtract them. So one of the things I want to show you is a proof for the first property, and you can use that same idea to do a proof for the second one at your leisure. So in mathematics, when we have a relationship like this that we say works for all x and y in the domain of your log function, then we want to show that it's true. And one of the ways you do that is you want to show that your left side is equal to your right side or vice versa. So we can start off here by saying let w equal log base b of x. So I'm going to take the first term on my right side, right here, log base b of x, and I'm going to assign it the letter w. And I'm going to say z is equal to log base b of y. Okay, so what that means is I can now take this form, this log form, and I can rewrite it as exponential form. So w equals log base b of x means my base is b, my exponent is the answer to my log, so b to the w is equal to x. And similarly over on this side, we have b to the z equals y. So now I go back to the left-hand side of my equation, and where I see x and y, I replace it with b to the w and b to the z. And somehow I have to make the left side equal the right side. So let's see how this helps us. So when I have a problem like this, b to the w times b to the z, my bases are the same, so I get to add my exponents. So I get w plus z. And now based on the property we discussed the other day, we have log base b of b to the w plus z. I just lift off my exponent, w plus z. Well, what was w and what was z? W was log base b of x, and z was log base b of y. So that's how you prove this mathematically. And that's when you get to do those fancy letters QED. That's what mathematicians use when they solve a proof. QED. It's Latin. Thus it is proved. Okay. You can use this same type of proof over here. Try it sometime, when you're home and your Xbox isn't working or something and you want to do a little mathematics. Okay. So anytime you see the log of a product, you simply write them as the log of each of the factors added together. And if you have the log of a division problem, it now is the subtraction of the log of the numerator minus the log of the denominator. And you'll be using all of these properties for about a half an hour today, so you'll get used to using them. Okay, another exponent property. Let's say we had a to the x raised to the y power. And I shouldn't be so messy. Raised to the y power. So how would I simplify this with my exponent rules? Yep, you multiply your exponents. The language we use for this exponent property is when you have a power raised to another power, right? A power raised to another power, you multiply your powers, okay? So again, there should be a similar log property for an exponential property, an exponent property, since they're inverses of each other. So let's take a look at our next property here. Here we have log base b of x is a power, and that's being raised to another power, the power of p. So this is similar to our power raised to a power. So what happens is that the two exponents multiply each other. So the p comes down in front. Notice this p comes right down in front and multiplies it by the exponent that's left, which is log base b of x, whatever that is, whatever log base b of x is. So here are your two exponents you're multiplying, p times log base b of x. This is one of the most useful log properties we're going to be using throughout the next week or so. We'll be using this quite a bit. So if you see something like this, log base 2 of 2 to the 4th, we know the answer to this based on the properties we looked at the other day is to simply lift off that exponent. But if we were to use this property to show how we get 4, it would look like this. The 4 comes down in front, and it multiplies the resulting log. Log base 2 of 2 is 1, and 4 times 1 is 4. So notice we get exactly the same answer. Now, if I had this problem and the instruction said find this log or evaluate this log, I wouldn't go through all of this because I can just look at this and know my answer is 4. All right, but I just wanted to show you with something you would understand, hopefully, how you could use this property. And again, this is used over and over again when we start doing all of our application work with logs and exponential functions. Okay, this property here is actually a formula, and it's called the change of base formula. And this is quite useful because, as you recall the other day, when we looked at our calculator, we only had 2 bases we could evaluate with our calculator. We had base 10, which we called the common log, and we had base E, which was the natural log. And those were the only 2 buttons on our calculator. So let's see, does anybody have lecture 35 notes available real quick? Okay, thank you. So I think there was a log on here with a different base. Okay. For example, we had log base 5 of 1/25. We had log base 36 of 6. We were able to find the answers with them based on the properties we learned, but let me show you log base 36 of 6. Okay, so we knew that the answer to this was 1/2 because 36 to the 1/2 power is 6. But let's see how we could use the change of base formula in case you forgot how to find this. So the change of base formula says regardless of what base you start out with, you pick a base, either base 10 for your common log. So here in that case, A would be 10, log base 10. Or you can pick the natural log, which is log base e, because those are the two logs you have in your calculator. So notice what it is. You decide what base you want to use, either base 10 or base e, and you divide, you say take the log base 10 of x and divide it by log base 10 of whatever this base is, b. Or natural log of x divided by natural log of b. It doesn't matter which one you use, and I'll show you that. So here, in this particular example, your base is 36. So let's use the common log. Let's find log of 6 and divide it by log of 36. Okay? Now we know what our answer is already. Our answer is supposed to come out to be 1/2 because we found that in Wednesday's class. So let's clear out our calculator here and say log of 6 divided by log of 36. There's your answer, 1/2. And the good news is it doesn't matter which base you use, the common log or the natural log. You say ln of 6 over ln of 36. Again, if you want to work on this, try to do a proof of this similar to what we did with that first property, and you can see why it doesn't matter which base you use here. And if you work on it and you can't get it, I'd be glad to show you the proof. All right, so natural log of 6 divided by the natural log of 36. Again, we get the answer 1/2. So you can pick your favorite base, either the common log or the natural log, and that way, no matter what log you're given to evaluate, you can use your calculator to do it. So this change of base formula comes in it's very handy. Those are the only 4 properties we're going to use today, those 4 properties. So let's take a look at a couple of examples of using these, and then I'm going to give you the whole rest of the period to work on an activity. So this first problem, number 2, says, use the properties of logarithms. So, okay, so you go back in your brain and you say, okay, I've got to use some property, and I want to combine this expression. So log base 4 of 2 plus log base 4 of 32. Now, some of you might be able to do this without any property. If you're really good at evaluating logs, you can do this without a property. So the first thing you say to yourself is, this represents an exponent, and this represents an exponent. When do I add exponents? I add exponents when I'm multiplying. So that might help you recall the actual property here. And I have to have the same bases. My bases are the same. Okay, so I can rewrite this as a single log. I can rewrite it as a single log with the base 4. And I say, and all you have to remember is, when do I add exponents? When I multiply. So you just multiply 2 times 32. You simplify 2 times 32 and call it 64. And now your job is to find the answer to that, log base 4 of 64. So this is where knowing a little bit of multiplication is helpful. You have to figure out, can you write 64 as 4 to some power? And what would that be, 4 to some power? 64. Third, yep, 4 times 4 times 4 gives you 64. So now that you have log base 4 of 4 to the third, you just lift off your exponent, and that's your answer, 3. Okay, so your answer to this is the number 3. If you wanted to do this a second way, you could use the third property we discussed today. You have a power to a power here, so have the 3 come down in front. 3 comes down in front, and it multiplies the log that's left. 3 times log base 4 of 4. Log base 4 of 4 is 1. 3 times 1 is 3. a couple of different ways you can do this problem. Any questions on that? How I got 3? And remember, you can always check your answer to a log problem because you can check it by writing it in exponential form. Your base here is 4. 4 raised to the third power is 4 to the third, which is what you started with right there. That's your input into the log function. Any questions? Okay, let's take a look at number 3. The instructions for number 3 are a little different. It starts off the same, use the properties of logarithms, but now you see the word evaluate. Here you saw the word combine, right? You're combining this into a single log. That's a little different than the word evaluate. So when you see the word evaluate, you want to just find the value of that log. So you see log base 3 of 81. So what's one way to do this? What's one way to do this? Is it log base 10 or log base E? No. Could you use something to, could you use your calculator to do this? Can you use your calculator to do this problem? How would you do it, Ben? Right, you use your change of base. That was one of the formulas we just looked at. You could apply your change of base formula to this. And Ben decided he's using the common log, so you take the log of 81 and you divide it by the log of 3. Okay, so base 10, so here we go, log of 81 divided by log of 3. Let's see what that answer is. 4. Oh, so that's my answer. How do you check it? You just said log base 3 of 81 is 4. So you check it by saying 3 raised to the 4th power is 81, and the answer is yes. Okay, so if you were actually plotting the graph of log base 3, 81, 4 would be a point on your graph. Your input is 81 and your output is 4. So if you were actually plotting this log, 81 would be way out here, woo, and you'd be at the point 4, knowing that 1, 0. So this would be log base 3 of x. That would be a function. And that's what the graph would look like. If you put 27 in here, you're at 3. Log base 3 of 27 is 3. So it grows very slowly. The log function grows very, very slowly as x approaches infinity. It continues to increase, but it's very slow. Okay. So that's one way of doing it, is with a change of base. How else could we have done this problem? Okay, so I heard Adam say 4 times log base 3 of 3. Now, where the heck did that come from? He rewrote this at 81 as the base 3 to a power. Okay, you want to be able to get 81 as 3 to some power, and he did. He said it's 3 to the 4th. 3 times 3 is 9, times 3 is 27, times 3 is 81. So now the power comes down in front and multiplies log base 3 of 3. Log base 3 of 3 is 1. 4 times 1 is 4. So that's another way to do it. Actually, can anybody think of a third way to do it, by writing 81 as a product of two numbers, where each number can be written as 3 to a power? Can anybody think of writing this another way, where the two numbers inside are 3 to some power? How about just any two factors of 81 that might be helpful here? 9 times 9, right, 9 times 9. So now we get to use our first property. We have a product. This equals the log base 3 of 9 plus the log base 3 of 9. The log base 3 of 9, 3 square is 9, so my answer to that is 2. That's the exponent I raised 3 to. Log base 3 of 9 is 2. And there's 4 all over again. So I've just done that one problem 3 different ways. Okay, so you have, sometimes you don't like it when you have choices. You just want one way of doing things. And I would encourage you, after you do the problems today one way, see if you can do them another way. Sometimes it's nice to have that flexibility. Any questions on evaluating log base 3 of 81? Any of the ways we just looked at it? I think some of you have already gone on and done the next one. So here we have log base 2 of 4 cubed. So we're going to use our exponent property where the 3 comes down in front and multiplies log base 2 of 4. Log base 2 of 4 is the number 2 because 2 square is 4. My answer here is 6. Okay, that's one way to do it. One way. Now here's another question. Can I write this as 2 to some power so I can just lift off my power and be done? Can I write 4 cubed as 2 to some power? Can I write 4 cubed as 2 to some power? 2 to the 4th? 2 to the 6th. How do you get 2 to the 6th? Because 4 is 2 square, right? So there's 4 cubed, and multiply these. So if I put that as log 2, log base 2 of 2 to the 6th, I lift off my exponent, there's 6. So 2 different ways to do the same problem. So the moral of the story, folks, is if you can ever write your input as the base to a power, you can be done just like that. You just lift off the exponent. Okay. So this one says use the change of base formula. We already used the change of base formula on this. This was done. Let's use the change of base formula on this one. I'll leave this to you to try. So let's use the change of base formula on this one. So suppose you forgot your property. You could do this log base 2 of 4 cubed is 64. So if we wanted to evaluate that, we take, let's use the natural log this time. The natural log of the 64 divided by the natural log of the base. You throw that into your, notice we are not taking the natural log of 64 divided by 2. This number is a constant, and this number is a constant. This is not equal to the natural log of 64 divided by 2. Those are not equal. Okay, this says it's just a division problem of 2 logs. So you put both logs into your calculator. Natural log of 64. And I'm going to divide that by the natural log of 2. We already know what our answer here is. It's 6, so hopefully our calculator will support that. And there's our answer, 6. Okay. So you could, again, if you remember your change of base formula, you could do all of these with the change of base formula as long as you had a calculator. If you didn't have a calculator, then you could use your properties. So right now you have a very long, wonderful activity that's going to help you to practice using these properties to expand and simplify log expressions, and just using them both directions. After you finish this activity, you should be pretty fluent with the log properties. Okay. And at first they're a little like, but as you do it, by the end of the hour today, you're going to feel a lot more comfortable with these properties. What is it? Is it Nike that says just do it? Oh, no. Is it Nike? Yeah. So Nike, just